Hi. Hello everyone. Welcome to information sharing session on failure analysis. In previous session, we understood that casting defects are rarely unintentional. They happen when certain processes in the manufacturing process aren't properly managed. A defect might be caused by a single, well-defined source or, more commonly, by a mix of causes. Only the most prevalent faults are selected for characterization among the various problems commonly encountered during traditional casting methods such as sand casting, die casting, and investment casting. We studied defects like shrinkage, gas defects, pinholes, and misrun. Today, we will study about hot tears and cold cracks. We will also study about primary processing defects, like rolling, seam, non-metallic infusion, delamination, and exfoliation. Hot tears and cold cracks. Hot tears, cold cracks, warpage, and other faults emerge as the casting cools from solidus temperatures to room temperature. Hot tears are crack-like flaws that occur when the mold is cooling or immediately after solidification. These fissures are quite uneven and have severely oxidized surfaces. Cold cracks are continuous, but hot tears are ragged or uneven. Hot tears are caused by three factors: internal strains brought on by restricted contraction because of mold or core resistance, internal stresses brought on by differential cooling because of poor casting design, and high pouring temperature. All of the casting flaws mentioned so far are often found by radiographic analysis. Primary processing defects. Rolling. Ferrous and non-ferrous alloy rolled bars are first cast as ingots or billets, and then they are hot rolled into a variety of sizes and shapes. The top, bottom, and areas that are typically prone to flaws like pipes and blowholes are cropped off. However, because of insufficient cropping, some of the flaws may still be retained. These flaws are prone to collapsing and extending in the rolling direction. The majority of these discontinuities, which are often oxide layers, always roll up from the outer surface to any depth. The best method of detection is a micro-examination of a transverse disc that has been sliced at various points along the rolled length. This imperfection is found using an ultrasonic flow detector. It would be possible to avoid this flow by properly cropping the top and bottom ends of the rolled length. Seam. Another typical defect is a seam, which is a discontinuity extending along the direction of rolling at the surface and is often recognized as one of the rolling flaws. It is caused by the folding and rolling of oxidized surfaces. The heat gradient during rolling is likely to cause cracks on the rolled bar surface. Although it is common practice to trim off the ends of rolls that are prone to cracking, residual cracks may remain in the cut ends. The Magnaflux check can simply and precisely detect seams and cracks on the surface or subsurface of steel bars. Visual and/or dye-penetrant checks, followed by light etching, disclose these faults in light alloy bars. Non-metallic infusions. Chemical substances and nonmetals are non-metallic infusions found in steel and other alloys. They are the result of melting and pouring related chemical reactions, physical consequences, and contamination. These infusions are divided into endogenous and exogenous groups based on their source. Endogenous infusions, often referred to as indigenous, develop naturally within the metal as a result of chemistry. These substances are usually quite tiny and precipitate upon cooling. Nonmetals become trapped and forming exogenous infusions. Their origin can include slag, dross, flux byproducts, and mold fragments, and their size varies widely. If the melt is dirty, the ingots produced during rolling will have irregular stringers of infusions made up of silicates, sulfides, and chains of oxide particles. Magnetic particle examination of steel bars displays these flaws as discontinuous straight lines. The intensity and spread of these infusions are revealed by a succession of step grinding and magnafluxing operations. Straight line signals might not be continuous, however chains of globular oxide particles that are present indicate continuous flow. Not all of these longitudinal infusions are dangerous, depending on how the product is used in the end. delamination. It is yet another significant flow on a sheet or plate. Because there are oxide coatings on the surfaces of the large blowholes in the ingot or billet, they level out during rolling and do not weld together. If necessary, the flow can be found by macro-examining the edge following light etching and polishing. In contrast to thin sheets, where it is not practical, thicker sheets and plates are better candidates for ultrasonic inspection. The ingot roll billet must be properly cropped at the top and bottom ends and examined using ultrasonography and macroetching before the corrective methods used to ensure freedom from the defect are discarded. Exfoliation. Even while it is not a common flow, it still frequently occurs in rolled or extruded goods made from specific aluminium alloys under particular temper conditions. The corrosion fault manifests as thick, powdery corrosion products that attack along the grain boundary which is parallel to the working direction. This causes a leafing effect when the grain deformation reaches a critical level with regard to grain size versus width, especially if the materials handled are in the T4 or T6 state. This fault is prone to increase. It is practical to conduct an ultrasonic inspection check to identify the beginning of exfoliation cracking. This deformity is fairly simple to spot visually or with a 10 times magnifier thanks to the presence of its distinctive traits. Micro-examination will, nevertheless, demonstrate the exfoliation's presence. Aluminum, copper or aluminium zinc magnesium alloys are heat-treated in the T73 condition, or the double aging procedure, to get around this. In next session, we will go through forging process defects. Thank you.